In this segment, we will be discussing about a concept which has often been discussed from the 12th standard itself, but not extensively, and that is about pulleys only, but with friction. When you solve problems related to pulleys in your 12th standard, they were always like frictionless. So means for example, suppose there is a pulley, it's a bad pulley. So suppose a pulley like that is there, and you are given with certain mass here and given with certain other mass here. So you always did that, right? So now suppose this was fixed like that. Okay, if it is so, then the tensions you always took same on both the sides, right? So this you said tension T, this you said tension T, and suppose both the masses are M and M, so both the tensions were mg, and then that you could do because you assumed that the pulley is frictionless. Now in this segment, we will remove that assumption of frictionlessness, okay, and that's a very important criteria, because generally there is another application, in fact. So this is one of the application where friction should not be there, as less as possible friction we should have, but there are other applications where we must have friction. So these are the application of power transmission. For example, suppose you are producing some power, and then you are transferring that power to some other point through a belt drive, So you have connected belts like that, and this one is say driving, okay. So this one is driving and this one is driven. It's like a gear drive. Gears are used to transfer power, right? And now when you have to transfer power over a long distance, so generally gears are not useful. So then in such cases you should use a belt drive, where what happens is at this location, if friction is absent, you cannot transfer this power. So friction is a very crucial means always we think that friction is a opposing thing, but here friction is a friendly thing, and then we are using friction to transmit the power there, okay. Now so for such applications, the concepts which are required, so those are the things of discussion for this segment, okay. And we will not get into the details of pulley drives, and there are a lot of complexities involved. We will take up the concept behind this pulley drive. So it will be more on, you can say that it's a concept of pulleys with friction or belt friction, okay, because there are many configurations which you can think of using pulley drive. So this is one which is called a simple pulley drive. Then you can have a cross. This is open, actually. It's called open pulley drive. Then you can cross them. So these things will be seen like that, okay. So you can join something like that and like this. So that's a crossed one. Or you can have, in fact, like gear trains, you can have, say, here another gear through which you can transfer maybe to one more location somewhere here, and so that could be a pulley here, okay. So like that, so that can be a compound case of pulley drives. So those, we are not going into those kind of things in this. Similarly, one more complexity can come in discussion when you have these belts, not flat belts, but there are some V-shaped belts. Then you can consider there, because these are rotating at a very high speed maybe. So the centrifugal action of the belts come into picture. So details are there and a lot of things can be discussed. If time permits, we can even see them in a different segment, but in this segment we are going to talk only about the simple concepts of pulley friction. Now when I say pulley friction, students generally have a confusion about whether the friction exists at this point where the belt or the thread is connected to the pulley, or the friction is at the pin joint where it is connected to the shaft or the axle. So that's a very genuine question which needs to be thought about and discussed. It's very important. Now the point is, if you have a frictionless contact anywhere, either on this part where the belt or the thread is in contact with the pulley, suppose that part is frictionless and you have friction at the joint, okay, at the axle, then it does not matter, right? It behaves as if it is a frictionless pulley. Again the tension will be same in this case. So that is not a case of pulley with friction. Now similarly, suppose you have friction here, it is almost they are not slipping with respect to each other. That means this belt or this thread is not slipping on the pulley, but you have completely frictionless bearings here on the joining point, okay. Under that case, again the tensions will be same exactly, because though here they will be in contact, but the tensions again will be same and the whole thing will behave as if it is without friction. So when we say with friction, that means friction must be present at both the places, okay. So the friction which is getting generated here should be or I should say that this bearing here or the joint here should be capable of applying that friction which is at the contact surfaces, okay. Otherwise, so you can think in another way, that the minimum of the friction is the friction which the pulley can offer, okay. Whatever slips first, so that is the friction which the pulley will be able to offer, okay. Now having said that, let's go and discuss the basic concepts behind this. So let me draw a bigger pulley maybe here, say okay, that's fine. Suppose you have a pulley here and we have wrapped somewhat like this, you know, so two belts, so like that. Okay. So it's a belt which is wrapped on this pulley, and you are applying say about this point certain moment. For example, you are capable of, or this joint is capable of applying a moment in this direction. Had it been frictionless, this moment cannot come here, and also this is capable of applying a reaction maybe, okay. So a reaction also can be applied by the ground. So these two things, the moment M and the reaction R are the ground reaction force and the ground reaction moment. Okay, reaction force, reaction moment, which I applied. And then now this moment actually is getting balanced by the tensions which are existing at these two locations, or these two parts. So say T1 and T2. Okay, now you see this, and then this is the first difference which comes as opposed to this case, where tension used to be always same in the case of frictionless pulley, and now the tensions are different, T1 and T2, and then they are required because, see, if you take a moment about this point, and suppose this is just about to now slip, it is just about to slip on that surface. So that means it is just on the balance. That means this moment is getting resisted by, suppose this radius is R, let me say suppose this is R, similarly this is R, okay, this radius is R. Then this T2, now T2 times R, suppose this tension is in this direction and this is in this direction, so T2 times R minus T1 times R. So this is the effective movement that is coming in this direction, and that should be exactly balanced by that M, isn't it, on the verge of slippage. If now slightly this becomes more, suppose we are applying a slight higher force here, then the belt will slip over this, okay, in this direction. So that's the way to look at the balance in this case, and depending on the angle of these two forces, the reaction also will be available here. That's not a very important thing for us now, because that is not in any way related to power transmission. Okay, so this reaction force should be studied in order to design the pin which basically should be used here. So it should be sufficient enough, its strength should be sufficient enough to withstand this reaction force R. Other than that, there is no such significance of this force R, reaction force. But more important is this moment, and which is caused by or which is resisted by the difference of these tensions, and that is why these tensions must be different. And then there is another way to look or interpret this in a way, what do I call, the change in tension is by looking at this example. I'll go to the other page and then I'll draw there. It is because it's a sort of digression, but it's helpful. Many times students face difficulty why the tension is changing and which side actually will be more, the tension force will be more. So to do that, let's see, suppose you have a case like this, suppose you have some blocks here, like that, okay, and you have strings connecting them, okay, and here all at places friction exists, and all of them may be mass m, okay, mass m. Now think about the forces which exist, the tensile forces that exist on these strings. When you suppose they are moving with so they are now moving with an acceleration, so that means this tension T here say this I will call T3, this is or T2, T1, T2, T3, okay. So this is say T2 and this is say T1. Now T3 is responsible for mass times acceleration, but now T2 is responsible for 2 mass times the same acceleration, because the whole thing is accelerating at a single acceleration, okay. And then now T1 will be 3 times m times the acceleration. So that means the tension keeps on increasing as you go to this side, okay, even if it is frictionless. So that's what I'm saying. And if friction exists, again that friction also keeps on adding here. So this one is acting against only one friction here, okay. So if there is a here the frictional force Fr, here again the frictional force Fr, here again the frictional force say Fr. Now this tension is working against all the 3 frictional forces. This is working against 2 and this against only 1. So the same thing happens in this case. If you think of these this part of strip of the belt which is in contact with the pulley, if you think of them as say small blocks, okay. So if you consider them to be small blocks, you know, and each one is contributing some friction force. So these friction force keeps on adding, okay, and that is how you at this point it will be the lowest friction which is being pulled on this tension, and then these frictions keep on adding, and then this side, if it is about to move on this side, okay, if it is that means the belt is about to rotate in counterclockwise direction, then the friction obviously will be acting in the other way. So let me draw the frictional forces. So at this location the frictional forces are like that, okay. So these are the frictional forces if the belt or the rope is about to move in this way, and then these friction forces will keep on getting added up, isn't it? So here this much friction, but here the tension is actually trying to carry out or move forward this tension plus this friction also. Then if you see at this point this tension but this much friction, so like that the tension increases and T2 will become more than T1, sorry, than T1. So that is another way of looking at or interpreting which direction the tension will be more. Or else this also should tell you that if moment is applied in this direction, obviously this has to be positive, so or in this direction, so positive negative you have to think in which direction you are taking as clockwise or anti-clockwise. So T2 has to be more than T1 for this balance. So whatever is comfortable to you, think in that terms, and so that will give you the idea about which tension will be more. And now to relate, now how much will be T2 with respect to T1? Is there any relationship between them? To evaluate that, what we should do is we can pick a particular segment of this, maybe say this segment, suppose we are considering, okay, and now I'll draw that here at a bigger scale, so that let's say that part is somewhat like this, okay. So that is that small portion, we have enlarged it, and if I extend these lines, obviously they will meet at the center O. So this center is this center O, fine. Now if it is like that, and let's say this angle is d theta, small angle d theta, then what happens is, if you take a tangent here, so the tensions, this doesn't look like a straight line, so let me draw like that. Okay, now the tension here would be working in this direction, and here it will be working in this direction, and these angles being d theta over 2 and d theta over 2. Okay, so that's how that means, so at this location, if I draw like this, you can realize what's happening. So from this point, you see, if you consider this, so this angle is d theta by 2 and this is d theta by 2, and this one is say t plus dt, and this is t. Okay, so we are considering basically this way of slipping, that is T2 is more than T1 sort of, and that means then the frictional force will be acting in this direction. Okay. Now, so because this is a small segment of area of contact, and we can now think that because of the normal reaction, so I'll draw the normal reaction here. Okay, and because of that and the coefficient of friction mu, so this frictional force Fr is acting in this direction, and the things are in balance, that means it is just about to slip. Then I think we can write, I'll move this part a bit, so that we'll get some space. Oh my god, so let's not move like that. So maybe here slightly, if I do, I may get something. No, still that's coming. Okay, let it be there, no issues. Let's let's write here the equations. Okay, suppose we balance the equation in the tangential direction. Okay, so what will be its component here? So this side, it will be t cosine of d theta over 2, right, d theta over 2, and this side it is and then the friction is in this direction, so plus I need some space. Okay, let me first write it here and then I'll copy it to the next page, so it doesn't matter. Then friction force should be equal to here t plus dt times cosine of d theta over 2. So this is the balance in the tangential direction, and similarly I'll just write it here, but then I'll copy it to the next page. And if we try to see the balance in the vertical direction, your that n should be equal to, you can call a small delta n or n, doesn't matter, should be equal to mu times or I'll say the frictional force, the frictional force will be equal to mu times that n. Okay, and yeah, that's fine. So that should be equal to that's fine. Or something else is missing. Yeah, I think their sign components also are missing, right? So not only this much, friction is this much, fine. So that will be okay. So here this portion should be replaced with that. But if we try to balance here in this direction, we should have n should be equal to t dt t plus dt times sine of d theta over 2 plus t times sine of d theta over 2, right. So these are the vertical, suppose we balance in the n direction, the normal direction, so this is the balance, fine. So now let me go to the other page with just the equations, okay. So here I wrote there because just to keep things on one page so that you will understand with the pictures. So we have these two equations now, balance in the tangent direction. So tangent direction, the balance equation becomes, say, t cos of d theta over 2 plus mu n, I am writing n here, should be equal to t plus dt cosine of d theta over 2, and in normal direction the equation is n is equal to t plus dt times sine of d theta over 2 plus t sine of d theta over 2, right. So these are the two equations which I had written there. So this is the normal direction and this is the tangential direction with Fr replaced with mu n, okay. So that's the whole thing. But then d theta by 2 is very small, isn't it? So in that suppose we in that limit, if we take these things in the limit of say when d theta tends to 0, let me take it there, okay. So what will happen is okay, so this will become what, t plus mu n, because d theta by 2 is very small, so cos d theta by 2 will become 1 in that limit. So this is mu will be equal to, say, t plus dt, okay. So now these two cancels out and you have mu times n is equal to dt, okay. So that's, say, equation number 1, and so this we got from here, and from here, say, now from this equation we can write that say n is equal to t times sine d theta by 2 in the limit when d theta by 2 tends to 0 is d theta by 2, and then this, you know, dt times d theta by 2, both are small quantities, so second order terms, so we are neglecting that, all second order terms, so that is gone. Then from here it becomes t d theta over 2, so that means this becomes t d theta, so that is equal to t d theta. So this is our second equation. So what we can do, we can put this here to mu times t d theta is dt, sorry, dt, okay. Now that means I can write this as say dt over t is equal to mu d theta. Okay. Now if I integrate this now from say T1 to T2, where the angle goes from 0 to beta, this full angle suppose it is beta, and theta goes from 0 to beta. What I will do is say here it is from T1 to T2 and this is from 0 to beta. Then you will get say ln T2 over T1 is equal to mu beta, right. So that means T2 over T1 T1 is equal to e raised to mu beta. Fine. Okay, so this is in a way the equation which you should be completely comfortable with. Okay, that means when there is a pulley and a belt which is wrapped about the pulley with an angle of wrapping beta, then the ratio between the tensions in the two sides is related to each other like this, T2 over T1. T1 is now see, and then please note that this angle beta is in radians. So many times students forget to use that beta in radians. So please make sure that you use beta in radians. Now this will be always positive, so e raised to some positive number, because this mu also is positive, beta is positive, so e raised to some positive number is a positive number. So T2 is equal to T1 times that positive number, so T2 will be more than T1. So that you should be very careful about which side you are moving and which side you are applying the moment, and that should tell you the ratio, proper ratio. And in fact, once we solve the problems on the belt friction, you will realize that decision, that in which direction you are actually trying to move the pulley, so that will decide this ratio, whether it is T2 over T1 or T1 over T2. That has to be very carefully chosen. Okay. So having, I think, so that's the formula which I wanted to derive, and so that is the concept behind any pulley drive systems which can be discussed in later segments. So see you in the next segment with some examples.